Recall that vectors are used to represent quantities that have both a magnitude and a direction. So we saw that we can use a directed line segment. The length of that line segment will represent the magnitude, and you can see its direction. It's pointing a certain direction. We want to be able to represent a vector with its components. In 2 dimensions, it will have a vertical component and a horizontal component. So if this vector is drawn this way, and we see that this is A units and this is B units, and I'm going to call this vector V. We can represent V this way as A comma B. And we can use these chevrons to denote the fact that we're talking about components of a vector. If we choose to move the vector such that its initial point is at the origin, so I can draw this vector, remember, keeping the direction the same and the magnitude the same, so that it is here, then this would be A and this is B. It is still our vector V, still with components A, B, but notice this terminal point would be at the point AB. We call a vector that has its initial point at the origin a position vector. So right here, V is a position vector. And its terminal point is at AB. When it's written in component form, it's also AB, but in those chevrons. So let's find the component form of another vector. Let's let the initial point of the vector be 5, -1. And we'll have the terminal point be 2, 6. And I'd like to come up with component form for that problem. So we're going to try to find AB in component form. Well, let's just draw a picture. We know 5, -1 is 1, 2, 3, 4, 5, -1. Whoop. We don't want the vector to there. We want the initial point there. Sorry. There's our initial point. It's the point 5, -1. That was not a vector. It's just a point. And its terminal point is at 2, 6. So 2, 3, 4, 5, 6. Here's its terminal point right here. So our initial point is at 5, -1, and our terminal point is at 2, 6. So we're trying to find the component form of this vector right here. And that's our vector AB, since this is our point A and this is our point B. Well, notice if we look at the picture, we can find the components. I can just count, even though I have to look past all that scribbling I did right there. I'm over here at 5. Notice the point, terminal point is here, so to get to this point from here, I would go left 3. So the x component is -3. And the y component now is the distance from -1 all the way up to 6. That distance is 7. So the vector AB is -3, 7. But look at where these values come from. Notice you can get this -3 from 2 minus 5. So I wouldn't really need to draw a picture next time. And similarly, this 7, where does it come from? 6 minus -1. And in fact, let's state that generally. If a vector in a plane has an initial point that is x1, y1, and a terminal point that's x2, y2, we can subtract the x components and subtract the y components, and we'll have our vector in component form. So let's just do it with this one. We don't have a picture to look at. So let's find the component form. We know it is, this is our terminal point, so it's -2 minus -7, comma, 13 minus 30. And when we do the arithmetic there, we have 5, what is that, -17. So we now know this is component form for that particular vector. Let's go on. Let's talk about scalar multiplication. We've seen in a previous video how you can multiply a vector by a scalar and what happens to it geometrically. For example, here's my vector. I'll put it in standard position or with the initial point here at the origin. And I'll just let that vector be v. And if you look at it, if this is 1 and this is 2, that vector in component form is 1, 2. But suppose we multiplied the vector by 2. Remember, geometrically that meant it's twice as long. We just extend it. Instead of being this long, however long that is, you could calculate it, it's twice as long. So in red, we have 2 times a v. Now let's look at what it looks like on the picture. If this is 1, this would be 2. This is 2, that would be 3, and this would be 4. And notice it looks like our vector is 2, 4. When we multiply a vector by a scalar, look at what seems to be the case. You multiply your x component by the scalar and the y component by the scalar. And that is in fact true in general. So let's state it officially. If u is the vector u1, u2, and k is a scalar, we can multiply each of the components by that scalar. So let's do this problem. U equals the vector 11 and -6. I'm asked to find -4u. That means I'm going to multiply 4 by the x component and 4 by the y component. And when I multiply those together, I have 44, -24. And it's done. Let's move on and talk about vector addition. And we'll start with these two vectors. U will be the vector 5, 1, and v will be the vector -2, 3. And let me draw the vector u with its initial point at the origin, so its terminal point will be here. So here's the vector u. And my vector v, remember when we're doing addition, the initial point for the first vector is here. Here it's terminal point. I'm going to put the initial point of my next vector right at the terminal point of the first one. So from here, I'm going to go in the x direction 2 units, and then in the y direction -2 units, and in the y direction 3 units. So from here, left 2 and up 3. 1, 2, 3. So my vector that is v will look like this. So the sum of those two vectors, remember you start at the initial point of the first vector and you go to the terminal point of our last vector, and we have u plus v represented. Let me draw this. This is our u and this is our v. And our resultant vector is here. But now let's look at what that is. What is u plus v in component form? It looks like this point or the terminal point is at the point 3, 4. Well, where did that 3, 4 come from? Well, notice the x components of u and v. In the first vector, we went right 5, and then in the second vector, we went left 2 for a result of 3. So in fact, u plus v came from 5 minus 2, or 5 plus negative 2, and the 4 came from the fact that we moved in the y direction 1, and then in the y direction 3 more. So the y component came from the 1 plus 3. So to add two vectors, it seems to be the case that you add the x components and y components together. And in fact, that's true. So let's state it officially right here. If u has the components u1 and u2, and v has the components v1 and v2, when you add the vectors, you add their corresponding components together, and then I tossed this in as well. When you subtract vectors, it turns out you subtract their corresponding components. So let's do a couple problems. We're going to calculate u minus v. So I have u minus v. That means I'm taking the vector 5, negative 4, and I'm subtracting 20, 3. So I subtract the corresponding components. So I have 5 minus 20. That's negative 17. And I have negative 4 minus 3. That's negative 7. And we have just done the vector subtraction. Let's do this one. Let me put a little space here so they don't run together. I'm looking for 3u plus 2v. So I have some scalar multiplication to take care of first. I have 3 times 5, negative 4. And I'm going to add that to 2 times the vector 23. We multiply the scalar by each component, so the first vector becomes 15, negative 12. And my second vector becomes 46. And now our vector addition says we just add the corresponding components. So in the horizontal direction, this vector would be represented by 55. And in the vertical direction, it will go down. Negative 12 plus 6 is negative 6. So if we were to draw this vector, it would have a horizontal direction to the right 55 and down 6. So I hope now you'll go work with some vectors and do some scalar multiplication and some addition and subtraction.